So welcome to the Homomorphic Encryption session, Transciphering. The first talk is secure and efficient transciphering for FHE-based MPC. So the speaker will be the Dr. Hoffman. The floor is yours.
So hello everyone, thanks for attending my talk, which will be about secure and efficient FHE-based MPC, so lots of keywords in one title. So we'll start by introducing those keywords. So first, I guess most of you are familiar with FHE, but I will still give a quick reminder. FHE is a way to perform operations on encrypted data. So let's say you're like an hospital, you have some scans of your patient, and you Is it good? Please tell me if the mic is not working at some point. So yeah, you want to send some sensitive medical data to a great startup that has a revolutionary algorithm to detect cancer or something. You don't want to directly send them sensitive data. You can encrypt them homomorphically, send them, they compute the operation, never decrypting the data, send you back the result. One of the issues with FHE is it's quite, like FHE ciphertexts are quite heavy. So it takes quite a bit of bandwidth to send, and it can also cause some computation client side. And one solution to this issue is to use transciphering or hybrid homomorphic encryption. The idea is, on the client side, you just use a symmetric primitive. So you have something lightweight. You send the ciphertext with, most of the time, expansion factor 1. And server side, the server does FHE magic, performs the transciphering operations, and retrieve an homomorphic ciphertext. So in order to do so, it needs to previously have received an encryption, homomorphic encryption of the symmetric key. And the idea of transciphering is it can homomorphically evaluate the decryption, the symmetric decryption, and the result of that is an homomorphic encryption of the result of the decryption, so actually an homomorphic encryption of the data. And then back to the previous protocol, you can do everything you want if you chose your FHE implementation properly. Let's now discuss the MPC part. So there exists some MPC protocol based on FHE. For instance, it's not the latest version of the slide, I'm sorry. For instance, there is one paper from Nigel Smart that propose a protocol or work with Nigel's paper. It also works with other papers, if there are so some days. And we don't get into detail about the MPC block. So we have some actors, they have FHE ciphertext that they send to the protocol, and the protocol do some stuff to do MPC. What is of interest of us is, with this protocol, you still send homomorphic encryption over the, you send homomorphic encryptions. So it takes like a lot of bandwidth, and one fix for the previous protocol was to use HHE. So our idea is to use HHE. So basically, no, every actor, instead of, it's not our idea, like the Nigel's paper suggested it. But if you do that, every actor now has a symmetric key. And when those actors use the protocol, they have to mix the symmetric key. And by doing so, they get some related key streams. Those related key streams, if they are malicious actors, they can control it. So basically, they can get encryption over with a key k plus delta, and they choose the delta. And we want our scheme to be secured against this issue. So one solution would be to say they just refresh the key often so that they cannot get like a full related key streams that they can control. But if you do that, you have to share the homomorphic encryption of the symmetric key a lot of time, and therefore it's not very efficient. Just a quick remark, this paper will mostly be in a static setting, so actors are always the same. if new actors come in, basically you can get, with more malicious actors, they can get an exponential amount of key streams. And what we show is not valid if they get an exponential amount of key streams. There is some discussion about the math that we may be able to use later to fix this issue, but all I will say from now on works in a static setting. So what are our contribution? First, we formalize a bit better than I just did, how using HHE in this protocol can be reduced to a related key attack security problem. So we need a scheme that is secured against related key attack. We show that Margaret, which is a scheme that was introduced in 2023 at Indocrypt, is resistant to RKA attacks without any change. So we just take the scheme as is, and we show that it works. And this scheme, when it was introduced, it was not implemented, it was not homomorphically implemented. So we provide the first implementation of the scheme. We show that it is efficient, and because we use some different techniques to evaluate it, that what was done before for this kind of scheme, we also adapt those techniques to Elizabeth and provide a new state-of-the-art implementation. So I will now describe Margaret, the stream cipher we use. Margaret is an instance of the mixed filter permutator paradigm. So what is this, the idea of this paradigm is basically you have a key register, which elements are in one group, and those elements go through various linear operations. So you take a subset of them, you permute the subset, you add them some random values, and you end up with a state at the entrance of the filter that is basically mixed key elements. They belong to G1. And the filter function is a nonlinear part of the scheme, and it outputs a ciphertext from another group. So both groups are not necessarily the same. In the case of Margaret, the first group, so the key elements are binary. The ciphertext are basically 4 bits integer, so you have like a modulus structure on it. And if you zoom in the filter function, it's a direct sum of 14 identical inner functions. And the inner function is just a lookup table. So why do we design Margaret like that? It's because the homomorphic implementation of Margaret is basically just implement the lookup table, which is not easy, but if you do it, all the other operations are linear and they're basically native in FHE. It's also convenient for the security analysis of Margaret, because the idea is you have your inner function, you derive some Boolean properties on it. With those properties, you can use some direct sum properties to bound basically the characteristic of the whole filter function. And with those characteristics, you can get complexities about like attacks that apply to our scheme. So because our ciphertexts are 4 bits integer and not just binary, it may be relevant for an adversary to look at them as 4-bit integer and not like 4 bits of ciphertext. So if we look at the attack path over 4-bit integer, it does not look promising. So our security argument is that if you take a random function that is like the inner function, the probability that it is a polynomial is extremely, extremely low. Using that, we need to check that the inner function is not a polynomial, so you can check that efficiently. And then you can use some code-based argument with the fact that there are very few polynomials to justify that it is far away, in the sense it does not share many outputs with a low-degree function. So you have a random function with no algebraic structure at all that you cannot approximate with a polynomial, so basically you don't have an attack path. If you look at the attack, or if you, sorry, it's a bit messed up. If you look at the attack looking at the ciphertext as just a binary output, then you can just study it as a Boolean function. So you compute its truth table. You apply Mobius transform to get its algebraic normal form. From this, you get the degree. You apply Walsh-Hadamard transform to get the Walsh spectrum. From this, you get the nonlinearity. And with that, you can get security against algebraic attacks, correlation-based attack. You also need to check a few things like number of monomials, which was a vulnerability of Elizabeth. But that's how we run the security analysis. Another kind of attacks we are considering are guess and determine attacks. The idea is an adversary is able to make a guess on the key. His guess will be low with like some probability, will be wrong with some probability, will be right with some probability. But if he makes the correct guess and the inner function has some vulnerability, its degree may drop like drastically with just one guess or just two guesses. So in order to ensure our inner function does not have such vulnerability, basically for every possible guess, we look at the subfunction it gives, and then we run the security analysis again. So it's quite a lot of computation because there are quite a lot of subfunctions with. But this is what we have to do to assert security. So why did I describe all the Margaret security analysis while we were initially talking about related key attacks security analysis? It's because if you look what a related key attack is in our setting, you get an encryption of a key plus something that you can control and that you may choose so that the security of the function drops as much as you want. The plus something will go like linearly in the linear part. And the question is, what will happen in the filter? And if you look precisely at how the filter is described, we show in the paper that basically something that looks like a combination of symmetric functions and differential of the filter function appears. That depends on delta, but delta will be chosen optimally for the adversary. So we can reduce the RKS security of Margaret to the regular, to the normal security of Margaret with a new filter function that can be chosen by the adversary. So how can we prove this security? We just prove the security for every possible function. So it becomes quite a bit of computation because if you remember, we had to prove the security for every guess. So now it's like every guess, every possible new filter function. So we reached like quite the maximum of what we were able to compute, like proving the regular security of Margaret with just normal C algorithm was a few hours. This was like out of reach. So we had to come up with a very optimized implementation of the Walsh-Hadamard transform. And I know that this implementation can be used for like leakage profiling application. So if you are doing that, you may be interested by just this implementation that we provide publicly. There's also another interesting link that we detail in the paper, which is that the RKS security basically grants the security against differential fault attacks if you flip bit in the key register at what time, like non-adaptative. You cannot flip a bit, look at the result, decide which other bit you flip. But if you say I flip any number of bits in the key register, I look at the output, it's basically a related key attack. So you have this implication. That is a useful link maybe for the CHES community. Sorry. Now let's discuss FHE implementation part. What we use to use for those implementation are something called programmable bootstrapping. It's something that can be chained, so you can do as many as you want. It really has this FHE like dimension, but it's limited to small lookup table, like maybe 4 bits, which have a bad cryptographic property, like some structure. For Margaret, we need to evaluate big lookup tables, so it's totally impossible to use PBS. We use different techniques, which is vertical packing. Vertical packing is efficient for evaluate big lookup tables, which is nice, but it's not efficient to evaluate 2 lookup tables consecutively because the input and the output of this operation is different. It needs, if you want to have two subsequently, you need to add a transformation stage in between, which is very not expensive. So it's, if you use this one and you want an efficient implementation, you will need something that is kind of leveled, which is fine for us because we know exactly like what a Margaret decryption is. And because the input of the output is different, the input is actually much bigger. So we have like a big key register. It's encrypted in a homomorphic way that is big. Let's take Elizabeth, for instance, because we implemented Elizabeth again, and it's pedagogic because we have both implementation, we can compare them. This is the inner function of Elizabeth. We don't really need to understand, we just need to see there are some S-box that are non-linear, there are some modulus for 4-bit additions that are linear. Before, all the S-box were a different PBS. So you take the input and you run them, and when you reach a S-box, you have to do a PBS, you can do the additions natively. If we evaluate Elizabeth with a vertical packing method, basically we just look at it as one big S-box. So we don't care what inside, there are some inputs, there are some outputs, and we just evaluate them in one go. So it's, in practice, it's a little bit more tricky, because there is a whitening step just before Elizabeth that mess up a bit with this filter, and the way we fix that is we dynamically update the lookup table with the stream ciphers, but the idea is still just evaluate the lookup table wall. And if you remember, I told you that Margaret, the difficulty of implementing Margaret was just to evaluate a big lookup table. This is what vertical packing do. So basically, our implementation is just evaluate the inner function. It takes 8 inputs. We get efficiently the 4 outputs. One limitation is the key is quite heavy, but it's still reasonably heavy compared to state-of-the-art other schemes. And we also have a protocol to somewhat fix this issue. We can work with regular key and add an expansion step that will transform them into the big ciphertext we need. If we do that, basically we win like 2 or 3 order of magnitude on the size of the key, and the total runtime it's more ×2 than ×3, but like this kind of order of magnitude. There are also some other optimizations that are useful. We adapt a known method that is called plain text independent transciphering, that basically allow us to use more plain text than what is natively supported by Margaret. And we also describe how to homomorphically do the key mixing protocol that is required by the MPC protocol. At some point, different parties need to mix their key, so we describe how they can do that homomorphically. I think on this version, I don't have the performance slide, I'm sorry, but the next talk will be 100% about that. But basically, we get a very good result about the latency, which is the amount of time we need to transcipher at least 1 bit. And we have a good result with the throughput, which is how many bits per second you're about to output. Yeah, that's it for me. Thank you. Do you have any question?
Thank you for the great presentation. And we have time for many questions. So is there any questions? So maybe I will start it. So is the status you have done for the Margaret can be ported to other stream servers as well?
It could be theoretically, but Margaret has this really nice property of being like natively secure against RKA without any modification. But what's good with this, like if you look at Elizabeth, Elizabeth is, for instance, an instantiation of a general paradigm. So maybe it will not work for the ciphers that are given already, but maybe we can find some different instantiations that verify this property. So there are not a lot of chance if you take something random that it will work natively. But
okay, thank you. So any other questions?
Yes.
I'm interested about your analysis between the RKA security against the DF8. Can you give more detail about it?
Against what?
Against the DFA, differential fault attacks.
Yeah. So basically, in the DFA model, you suppose that an adversary can some bits flip in the key register. So if you look at most, like that, there have been a few papers looking at DFA on Elizabeth, DFA on Philip. Most of the time, the idea is they guess where the bit flip happened, like they don't control where the bit flip is, but looking at the data, they can get a 100% guess of where it happened. And then they use this kind of differential attack like regular path. But when you have RKA security, what you say basically is you let the adversary choose which bits he will flip. He can flip like the amount of bits he wants, wherever he wants. So if it happens randomly, it cannot happen at worse places that when the adversary can choose. So RKA security means basically security against any kind of bit flips, but it does not work the other way. It's not because you have DFA security that it means that an adversary will not be able to have like the exact bit flips or that will work.
Okay, thank you.
So we still have time. Is there any other questions? If no, let's thank the speaker again. So now we move to the second talk of this session. It's a SOK paper, FHE-friendly symmetric ciphers and transciphering. The speaker is Dr. Chao Niu. The floor is yours.
Hello, everyone. Good afternoon. My name is Chao Niu from INT Group, and this is a joint work from Shandong University and INT Research. Then we will give this talk about the SOK for FHE-friendly symmetric ciphers and transciphering. First is the overview of this talk. We will give the background needed and the SOTA transciphering methods. And finally, we will give the benchmark metrics about this work. Then we will go to the first part. We will introduce homomorphic encryption and define their ciphertext expansion. Homomorphic encryption enables additions and multiplications over encrypted data. So modern FHE schemes like BFW, BGW, and CHES are support for SIMD style packing, so they can operate a vector in the same time. So the throughput is good. Then the TFHE support the Boolean gate operations for 1-bit data, or you can say the small bit width input. Homomorphic encryption allows us to protect users' data even when it is being used. So a lot of applications have been exploited for such as the privacy preserving, machine learning on the server, and also the statistics of the user's data computing on the server, like genome-wide studies. Then we will define the ciphertext expansion for these schemes. First is TFHE. TFHE support Boolean gate for binary data, or we can say the small bit width data. And the SIMD style packing is not allowed. So this scheme maps one element into a vector. So we can say BFV maps n inputs messages to only one polynomial plaintext. So the SIMD style packing is allowed for operation multiple datas in one instruction. Similarly is the CHES scheme. It supports for a complex number of half n to map into a polynomial. Next, we will get into the details. We can say TFHE map one element into a large vector and one element B, and every element in this form are of the size scaled m. We can say that this scaled m is much larger than the message itself, so the expansion of the ciphertext is coming from two ways. The first is the element to vector expansion. Next is the element expansion itself for the scaled message. So the typical expansion is over 1,000 times overhead. Of course, TFHE support for arbitrary lookup table while you are doing the bootstrapping operation. Next, we define the BFV expansion. For BFV, n messages are mapped into one polynomial m, and this plaintext polynomial m then encrypted as A and B. So the scaled expansion is also exist for the much larger dirt m than the message polynomial itself. We can see the plaintext format for BFV is in this form. The noise is at the least significant bit of this plaintext, and the message is scaled up to the most significant bit of this polynomial. So the expansion is the middle part of this plaintext. Similarly, CHES encrypts multiple messages into one polynomial plaintext. So its messages and the noise are both at the bottom of the plaintext, but the expansion of this scaled message is also exists because CHES need to control the noise by the scaling style noise management. So the ciphertext coefficient is also large. These two schemes have a typically expansion of over 80 times. So next, we will see the element to vectors expansion is not exist in this case, so the packing helps a lot. Next, we will introduce the drawbacks of FHE. The first is slow encryption at the client side. The FHE encryption in client side for the ciphertext encryption is typically 3 orders of magnitude slower than symmetric encryptions. And the next is the large ciphertext expansion. This expansion is from 10 times to 10,000 times according to its parameters for operation and its encoding methods. This kind of expansion costs a large memory and network bandwidth overhead. And this case will be worse when we encrypting the small messages because the packing is not can be done. So we can see that the server side overhead for FHE can be solved by GPU and hardware accelerations, but this slow encryption at the client side and the large ciphertext expansion cannot be fixed in accelerations. So how to do that is the solution. We choose the Transciphering. With one-time setup, the client sends its symmetric secret using the FHE encryption to the server. And the server have this FHE encrypted symmetric secret. So then the client can do symmetric encryption to encrypt its messages into symmetric ciphertext. Then this ciphertext are sent it to server to operate a symmetric, homomorphically symmetric decryption using this processed symmetric key, and we can obtain the FHE encrypted messages. So you can see, in this case, the client is light and the server is heavy. Next, we will define the SOTA transciphering methods. The combination of symmetric encryption and homomorphic encryption. This combination is according to the data shape and the volume. As talked before, we can use symmetric encryption at the client side, so we can get low bandwidth and fast encryption speed at the client side. Once we upload these messages onto the server, we can do TFEG-based transciphering for bit-level messages and obtain short messages and low latency. And we can do real-to-finite field, we call RTF transciphering for FP ciphers, encrypted data. And this kind of transciphering method wins at a batch throughput. The last is pooling to real transciphering. We can do CHES transciphering directly to convert AES encrypted ciphertext into FHE. So after server obtains the FHE encrypted messages, we can do the encrypted computations on the server side, the FM. Then we will send this FM encrypted by FHE to the client for the decryption to obtain FM. We will introduce the datasheet methods. First, if we use messages format of bit level input and the data volume is short messages, so we use TFEG paired with FHE friendly Z2 ciphers like Rasta, Philip, and Creview. Then for a large data volume, but the bit level data, we use the BTR transciphering to directly transcipher AES into CHES FHE ciphertext. So the last is the numerical operations and FP data. We use RTF to transcipher the FP encrypted symmetric data. We use Rubato, Hera, and Pasta. So we can see both transciphering methods and applications are run under the same FHE scheme. So the combinations is according to this matter. Then we will come into the benchmark metrics, including server-side transciphering performance and the client-side symmetric cipher performance. Last is end-to-end application after transciphering. We divide the server-side transciphering into two parts. The left figure is TFEG-based transciphering, and the right side is the packing-friendly transciphering. First is the low latency short messages combinations with TFEG-based transciphering. We can see the left upper of this figure is better. Marguerite talked before, and the Philip threshold XOR wins this package because they can produce 1 bit within TFEG bootstrapping, because the primitives they use are very cheap in FEG. We can see this matrix. The CMUX gate is much lighter than Git bootstrapping and the functional bootstrapping. Then we will come to the slowest one for early design, like Rasta, low MC, also the Philip direct sum. They have a lot of bootstrapping gates, so the performance is disaster. In this case, bootstrapping count matters, but not the depth. Then the AES transciphering, it performs not badly because there are over 10 years of optimization. In this TFEG-based transciphering, the throughput is roughly of hundreds of bytes per second, so it is practical for short messages. Then we will come into the SIMD packing friendly transciphering for high throughput. Rubato wins this package because the novelty of discrete Gaussian nodes added at the end of the encryption. Because this discrete Gaussian nodes, the security is enhanced very much, so we can reduce the round of this cipher. So reduced round means less homomorphic operations, so the performance is good. Then we come to the Hera wins master and the pasta because Hera has FEG-friendly linear layers, only contain additions and rotations, several rotations. So we also make a fair comparison for different variant of master and pasta for a deeper round and lighter state. So we can say the smaller state but a deeper round wins at better latency. Then is the last one for AES to CHES transciphering, because this is slow in this package, but the throughput is even 100 times compared to TFG-based AES transciphering. So we can see the next part is the symmetric encryption performance on the server side. This is simple because each FEG-friendly call contains several PRG calls for those FEG-friendly ciphers. So it means we run one FEG call contains several PRG calls. So the performance overhead is for the randomness in these FEG-friendly ciphers. So the challenge is how to balance the performance and security. We can say the AES leads the way. Then we come to the end-to-end applications. We benchmark the ResNet 20 inference for a CEFA 10 dataset for the setting of small data but high latency. For a large data scale, we use this genome-wide association studies at IDAS 2018. In this case, each nucleotide polymorphism are encrypted as 2 bits of 0, 1, and 2. And the total data volume is about 800 kilobytes. In this experiment, we can say the RTF for FP ciphers wins at batch inference because each RTF transciphering can transfer hundreds of images per transciphering. And for AES transciphering, AES CKKS transciphering, about 40 images per transciphering. Because this is because AES to CKKS transciphering has a problem of slots underutilization because each slot is only encrypt 1 bit in this case. Next is the large data volume and the low latency applications. In this case, FP plus RTF transciphering even also have the expansion. Even we used the transciphering, it has data bloats because each slot only encrypts about 2 bits, but each slot can encrypt an FP element, so the slot is empty in this case. It's about 8 times bloats. For AES plus BTR transciphering, the data format is flexible because we can restore the numbers from bits after transciphering, so there is no expansion. So we come to the observations of this work. First is the data shape role in the transciphering is the key matter. First, I think the data volume is, the split line of the data volume is about 1 kilobytes. Below this data volume, we can use TFEG-based transciphering. And if you have more data, you should use packing-friendly transciphering methods. So we can have this balance of latency and transciphering throughput. Next, go to FP ciphers. They have potentials but and pitfalls because FP ciphers wins at large volume transciphering, but the concern remains to their security and client-side overhead. Next is new design. New design for Z2 designs. This demand is because we can see the Z2 ciphers for BTR it still suffer from transciphering latency. So we need a new design like to have a much better performance than AES. So all in all, AES performs reasonably well because they have a heavy optimization. Thank you.
Thank you for the presentations. And we have time for questions. So, yeah, please.
Oh, thanks for the nice talk. So my question is about the last slides that you mentioned about the performance of the AES or transciphering for some scenario is not bad. That's my understanding.
Yes.
And yeah, I know there are lots of lightweight block ciphers after the proposal of the AES. And do you think that they would perform better than AES or not? Not much.
I think the design for lightweight is for the hardware or other matrix. For FHE, the design matrix is quite different. In the early age, the design matrix becomes the multiplication depth for FHE because the depth is very expensive resources in FHE. As we can see in this talk, the design matrix of symmetric designs aided for the FHE usage. The matrix is changed because the newly proposed bootstrapping schemes or schemes for noise controlment. So I think the design should consider FHE properties more. So
yeah,
so
thank you
it's
very
a
much.
complex question.
Basically, my understanding is that the depth of the depth may be the one important metric, right?
Yes, but there are two schemes, two kind of schemes. For TFE based, the depth is not the problem, but for SIMD packing friendly like CGKS and BFV, the depth is very important. So the design matrix is different.
Yeah, thank you very much.
Thank you. And is there another questions? Since it's a SOK paper. So I do have questions. So when you're describing the result of different sites like the CMD packing for the server side, the AES is at the right bottom part, and for the client solutions, the AES is kind of with good performance result. So what's the reason behind it?
Yes, this is a good question. For the server-side performance, the FHE implementation of AES circuits is very hard to design, and as we all know, the AES circuit is complex than most of the lightweight symmetric encryptions. So because the FHE only allows for limited computation operations type like additions, multiplications, and rotations. So for FHE, the AES circuit is very difficult. So the performance may be some kind of slow. But for symmetric encryption at the client side, the AES is under heavy optimization. So for ASNI in CPU, so the client side performance is good in reasonably.
Got it. Thank you.
What's more, it's this point of each FHE friendly call will contain several PRG calls. We can see the AES can form the PRG. So the FHE friendly designs is times of AES.
Thank you. And I have follow-up questions. So if, since it's a SOK paper, so if you have the freedom to design a cipher, which is perfect for transciphering, what might be the property of it for the both server side and client side?
Okay. I think for the client side, we should reduce the randomness because this will reduce the PRG cost. So the client side performance will be better. And for server side, I think the newly feature of FHE should be considered, like a new bootstrapping method or other schemes. So this is the answer.
Thank you. And is there any other questions? If no, let's thank the speaker again.
Thank you.
And for the last talk of our session, the speaker will be the same. Congratulations. And the title of the talk is XBoot, Free XOR Gates for CKKS with Application to Transciphering. The floor is yours again.
Okay, thank you. Good afternoon again. And I will give this talk about an optimization for CKKS bootstrapping with free XOR gates. Also, this work is done during the SOK, so let's get started. Then we will give the technical overview of this work. We achieved the free XOR gates for CKKS, and this is from the observation of extensive XOR is equivalent to the LSB of the accumulated integer of this form. So we will introduce later. Next, we will fusion this XBoot into the CKKS bootstrapping. So we can say, we call this free XOR bootstrapping XBoot. Next, once we obtain the free XOR bootstrapping, we application to the Transciphering, because Transciphering contains a lot of XOR gates, like AS of more than 20,000 XOR gates and 9,000 other gates. For Rasta, there are over 500,000 XORs. So these are all free with XBoot. Let's get started from the background of CKKS. CKKS allows an inverse discrete Fourier transform to map these vector messages from a complex number of half n into one polynomial ring. So we can say this equation for M equals inverse discrete Fourier transform for the vectors of messages is achieved. So after we obtain the plaintext polynomial M, we can encrypt it into A and B, also in the polynomial field. So the encrypted ciphertext format is as follows: A multiply S and add B. So we can say the plaintext M is much smaller than Q, the modulus. So we can obtain the CKKS plaintext format in this form. The noise and the messages are at the least significant bit of its plaintext. Once we have the inverse discrete Fourier transform for encoding, we can get the slot-wise operations to operate the vectors of messages. For conjunction and rotation, we do not consume levels, or we call the modulus, to control the noise. But the key switching operation is required. For the multiplication, we need to have a rescaling style noise management. So the modulus of CKKS will decrease because of noise management. So one multiplication consumes one level or one depth. So as the depth consumed, so the modulus of CKKS comes into the lowest level, or we call the shortest level. So the operations is not allowed for further for further computations. So we should to operate the bootstrapping operation. The bootstrapping operation is to regain the levels for noise management. So the task is to increase the Q for modulus. Let's get some details for the ciphertext at the lowest level. The polynomial are modular Q0 of this form. M are modulated by the Q0. We can see the message is much smaller than Q0. Then the task of bootstrapping is to regain the levels, or we can say view the Q0 as a capital Q of much larger size than Q0. Because of this modular reduction of Q0 is not applied, so the message becomes in this form for M plus Q0I, where I is an integer coefficient polynomial. Then we will have we have to operate the modular reduction operations of this form. Unfortunately, the CKKS scheme does not support for modular reduction operations, so we should to find some operation to do the modular reduction. In this case, we use the sum function of period Q0 to operate the modular reduction operations. So we can say after this figure, we can obtain the modular reduction Q0. So we remove the redundant part of Q0i and got the M for further computations. Of course, during the modular reduction, the operation field is changed because we should first change the slot encoding into coefficient field to operate the mode raise operation. So the vector of messages, they are operated a discrete Fourier transform to change to this polynomial M, and we operate the mode raise operation to obtain the M plus Q0i in coefficient field. But the same D-style packing operation for CKKS need to operate at the slot field, so we should convert the coefficient field messages into the slot field by using the homomorphically encoding operation, like inverse discrete Fourier transform. For this operation, we can get the vector Z plus Q0i. Then we can operate the modular reduction of interpolated sum function for operation the modular reduction operation, and obtain the vector Z to further up commutation. This is the full procedure of bootstrapping. Then we introduce the Boolean CKKS, where the XOR consumes one multiplication and one depth. In original CKKS, the message and the noise are at the least significant a bit of the plaintext. So we can say this x equals 3.1415. Green color are the messages of floating point. And the x-axis is the noise because the precision cannot covered. So in Boolean CKKS, only we want is the 1 bit of integer part of 1, and the fractional part of non-zero we call the epsilon is considered noise But in original CKS, this is the precision can cover this part of the epsilon. So we call the epsilon is the emulation error, because we must to emulate a Boolean value using a real value. So the 1 bit is represented using 0 plus epsilon and 1 plus epsilon, because the b is a real value. So this epsilon is coming from this. Next, once we have the Boolean value defined in CKS, we can define the arithmetic operation for Boolean gate. For not gate, we use 1 minus b. If b is 1, so we get 0 is the not gate. For XOR gate, we use a square a minus b. If the a and b are both 1, the XOR result is 0. Exactly the result of this formula. So we can see not gate not consume multiplications, but XOR gate consumes 1 multiplications. This is because the XOR requires the message and the GF2, but CKS does not support the GF2 message field, so the multiplication will be needed. Then we introduce the XBOT. We can see the XOR is heavy in many circuits, such as AS for 20,000 XORs and other gates for only 10,000. And XOR is free in MPC and the BGVBF way with specifically designed message space. So all we want is for a free XOR in CKS. So we think this is the design gap. But how to change this square x minus y into x addition y, which is FEG friendly operations? This is a hard problem. So we have this challenge for CKS. Then the observation comes for the extensive XOR gate for 1 plus 1 plus 1. The result of 1 XOR 1 is 1. So it's equivalent to the LSB of the accumulated integers 3. What I mean is the least significant bit of 3 is 1 is also equal to the extensive XOR. So we have this observation that if we can achieve LSB in CKS, so we can obtain the extensive XOR in CKS. So, but how to extract the LSB with CKS? It's a problem. Recall that during computations, the modulus of CKS will decrease because the noise management. So including the bootstrapping operations, slots to coefficient. So we just fusion this LSB into the slots to coefficient operation. So as you operate the slots to coefficient operation, the modulus of CKS will decrease and get the lowest level at Q0. And we carefully design the size of Q0 and the integer messages of yellow part of the higher order bits and the green part for LSB of this integer. So once we get the lowest level, only the LSB of the integers will be contained, but the higher order bits of this integer is of multiples of Q0. So the higher order bits is reduced by the Q0. By doing this, we can get a LSB in CKS. So let's have a full view. In this work, we change XOR square x minus y to x, add y first, and then extract its LSB in bootstrapping. So after the slots coefficient, the LSB is extracted. So then we want to is just bit bootstrapping to handle the emulation error epsilon. Then with this operation, we export. We achieved free XOR in CHES. Also, the interleaved AND and the XOR are supported because AND does not influence the LSB of the result. So we can achieve free XOR in any circuits to just replace the XOR into addition without redesigning the circuits. So this way is very elegant. Next way application is to Transciphering. In this work, we implemented the AS Transciphering for 16,000 AS blocks per Transciphering within 253 seconds. This is achieved by the free XOR, so the free AS linear layers, and also the smaller parameters because the depth of the AS evaluation is much reduced, so we can shrink the parameters of CHES. The next is the zero cost for linear layers or for the Rasta 6, and we achieved 303 seconds. First is the AS Transciphering. For AS Transciphering, the original method requires about 9 depths per AS round. In this case, all these shift rows, mixed column, and add round keys. Also, the cleaning operation for 2 depths are now free in export. So each round only consume about 3 depths. So we can achieve 1,200 seconds to reduce to the 36 seconds, and we achieve 5 times speed up for the latency and 2.5 speed up improvement for the throughput. Then for the Rasta, in Rasta, a random metrics are evaluated in each round, and the dimension of the matrix is very high, about 351. So the XOR in the matrix is very large. In this case, to evaluate the random matrix, we consume about 9 levels per round, and a large number of multiplications will be consumed because the XOR consumes multiplications in baseline. So it's about a very large. So the performance is disaster. In exports, all these XORs are free now, even for the XOR in nonlinear function, CHES function. We can see this. These XORs are all additions now. So with this improvement, we achieve over 10 times speed up. This is the comparison of existing result. There are split line for Transciphering using AES. We think below the 1 kilobytes data volume, we prefer the TFHE based Transciphering because the TFHE has a lower latency. So we can use TFHE for short messages. For CHES based Transciphering, we recommend for a large throughput case about monetized Transciphering, 14.4 milliseconds per AS blocks. For Rasta Transciphering, we bring the Rasta, the top of the FHE from the Z2 ciphers because of XOR free. So in this case, Rasta have 18.5 milliseconds per block. and higher throughput than AES transciphering because each block of raster is of 351 bits. In this work, the multi-threading was applied. We will have a summarize for this work. Achieved free XOR in CHES. Also, the interleaved AND and XOR operations are supported. So this work is fully compatible with bit bootstrapping. So we achieved the state-of-the-art transciphering performance for AES and Rust. There are also new symmetric design requirement for XOR is also expected for reducing the bootstrapping requirement. In current design, we also need about 64 bootstrapping per round to run AES transciphering. So reduce the bootstrapping number is very important. Also, the innovative structures like transistors is also good for lower latency. So this is references. Okay, thank you.
Thank you. Thank you for the great presentation and the great work. So if you have a lot of contribution in one work, split into 2 papers. We got it. So is there any questions?
Hi, thank you for the talk. I have a question about the interleaved XOR and AND. I suppose you implement the AND with the multiplication, right?
Yes.
And if you do a lot of additions before, you have to be somewhat careful bounding your message and the error to preserve correctness if you have a lot of them, right? So
yes,
you mentioned
this is the
20,000
point.
XOR operations. Do you always do a bootstrapping for the transciphering after the XOR operations, or did you increase the modulus? Did you mix both techniques? How did you deal with this?
Actually, the AND gates is implemented using multiplication, so the accumulated integers will become large if we have a lot of XORs and AND gates. So the noise is very large. I mean the emulation error for Boolean CHES.
Yeah.
In raster case, we increase the modulus for about from 30 bits into 40 bits to control this large integer errors in Boolean CHES. So.
All right, thanks.
Thank you. Is there any other questions? If no, I do have another question. So as you mentioned in your previous talk, the SIMD packing is very important for CHES and also the server side. So how about the CHES SIMD packing for the latest work, the last presentation, the scheme you proposed? Can you use it? Or?
Yes, we designed free XOR bootstrapping for CHES, and also the SIMD packing is allowed because the CHES support it. So as well, we support it too.
So now you solve the problem on the server side and client side. You can have good performance at both sides.
In this work, we only improve the server side improvement. So
Okay.
for the client side, AES is fast.
For the client side, AES is still faster.
Yes, yes.
Okay, thank you. So any other questions? If no, let's thank the speaker again, and let's also finish the session. Thank you.
Thank you.